Hello, and welcome to this recorded e-learning about the Spartan-6 clocking resources. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the clocking generation capabilities in the Spartan-6 FPGAs, including its new DCM functionality. It also explains its global and I/O clock routing resources. This module also provides some recommendations about getting the most out of these clocking resources. Spartan-6 is an unusual FPGA architecture. It contains some of the features of Spartan-3 and Virtex-6 device families. It is still a low-cost device family, but has some of the newest features in the FPGA industry. In this module, we're going to describe the global and the I/O clock networks in the Spartan-6 FPGA. We're going to describe the clock buffers and their relationship to the I/O resources, and describe the DCM capabilities in the Spartan-6 FPGA. Note that this module does not discuss the PLL functionality, which will be necessary to you, so please refer to the Spartan-6 user guide to learn more about the PLL functionality. Spartan-6 has two different clock networks, global and the I/O clock networks. Spartan-6 does not include regional clock networks like Virtex-5 or Virtex-6, which is a notable difference if you're used to working with those device families. The global clock network supports up to 16 global clocks and provides performance at up to 375 MHz. Spartan-6 I/O clock networks are used for distributing clocks to the IOB resources, which contain the SerDes functionality and operate at very high speed, in this case over 1 GHz. Now there are 4 I/O clocks per half edge and 2 I/O clocks that span the entire edge of the device. Spartan-6 also includes 2 DCMs that are commonly called digital clock managers, and 1 PLL or phase lock loop per clock management tile, which is commonly known as a CMT. The CMTs are a combination of analog and digital technology. That is, the DCMs are used to remove the input delay of a clock brought into the FPGA, as well as for clock generation. The PLL does not provide division capability, fine phase shifting, or complementary outputs. That is all accomplished with the DCM. This module will introduce the DCM functionality, but unfortunately we don't have enough time to discuss the PLL features. To learn more about the PLL features, please consider attending the Designing with Spartan-6 FPGA Device Family course, or refer to the Spartan-6 user guide. Spartan-6 is a wire bond type device. This means that the I/O pins are distributed around the periphery of the die. This implies that each pin is associated with an I/O bank on the perimeter of the device, like the Spartan-3 device family. But unlike Virtex-5 or Virtex-6, which have I/O banks placed in columns throughout the FPGA. This also places some restrictions on clock input pins. Spartan-6 has 8 global clock input pins per edge of the device. The global clock pins are really more like clock-capable I/O pins, which are regular I/O pins with special routing resources that allow the input clocks to get to the CMTs, that is the clock management tiles, which are located in the center of the die. Most of the CMTs are in the center column of the die, a long way from the I/O pins. In Spartan-6, the global clock input pins are the only pins that should be used for clock inputs. That means that the clock input pins should be used for both global as well as I/O clocking. There are no dedicated I/O clocking input pins. Each clock input pin can be used as a single-ended clock input with the iBuffG primitive used for instantiation. Adjacent dedicated clock input pins can be used for differential clock input pins with the iBuffDS primitive used for instantiation. The global clock pins are numbered 2i and then 2i plus 1 would be the corresponding adjacent pin pair. As an FYI, if you don't use the dedicated clock pins for clocking, you can use them for regular I/O. The pins can support any I/O standard that is compatible with the I/O standards used in the same bank. This is required as part of the I/O banking rules. These rules require that input pins share the same power supply in a single bank, and that output pins share the same power supply as well. To help with planning your I/O pin layout, I recommend that you listen to the Architecture Wizard and Pin Ahead recorded e-learning module to learn more about the benefits of using the Pin Ahead utility. When using a smaller density Spartan-6 device, there is one I/O bank per edge. You should also note that the 8 global clock pins are in the same I/O bank, even in the larger densities, so pay particular attention to this bank when planning your design pinout. Global clock networks can distribute a clock to every synchronous element in the device. This includes registers, block RAM, DSP slices, cores, I/O blocks, clock dividers, and SerDes resources. The dedicated clock pins allow for the input clock to route to the center of the device where the CMTs or clock management tiles are located, and then connect to the dedicated global writing resources, which are accessed with a buff-gmux primitive. This allows the clock to distribute throughout the die, effectively on a big fat wire. While technically Spartan-6 devices have clock regions, it is not as important since all 16 global clocks can enter all clock regions. We will see that there are a couple of places where the clock region concept might still matter. Like Vertex-6, the clocks are routed vertically through the center spines, then connect horizontally to horizontal clock rows called buff-H's, which are at the intersection of the vertical spine and the horizontal clock rows. The buff-H primitive does not support a clock enable functionality, so it is simply just a buffer. The global clock routing resources can drive either a clock or a reset port on every synchronous element in the device. This allows it to distribute a global reset signal. Note that driving more than one global reset signal on a global clock network is not recommended in Spartan-6. Also note that global clock networks cannot reach any other ports on the FPGA synchronous elements. That is, they cannot drive the clock enable inputs of the slice or data inputs of LUTs. This slide shows you a representation of the intersection of the vertical spines with the H-clock rows. As you can see, the H-clock rows are basically an extension of the global writing resources. Each of these 16 2-to-1 muxes can be configured to take its input from a CMT or the vertical spine, which would come from a dedicated clock input pin. Each H-clock row is either adjacent to the PLL or both DCMs in a single CMT. Direct connections from the CMT allow for more than 16 clocks per device. To connect a CMT output directly to an H-clock row, you will need to instantiate a buff-H clock buffer. This is a simple buffer with no attributes. Just connect the I port to the desired DCM or PLL output and use the O port as a clock signal. Clocked elements connected to that clock will then be restricted to one row. Using the direct connections from the CMT to the H-clock rows can be complex and should only be used when it is necessary to access more than 16 clocks. The buff-H instantiation is required here, but is not recommended in any other context. This is because the buff-H is only partially supported in the Spartan-6 FPGA. At the bottom of this slide is a representation of the vertical spine inputs. As you can see, there are 48 inputs available to the vertical spine. 16 inputs from the left and right edge of the die, 16 inputs from the top and bottom edge, and 16 inputs from the CMTs and/or internally generated from the FPGA logic. In the end, understanding this is not significant, but it does show you the possible sources of clock and reset signals that you can have.